Hi.
Hey, everybody. So today we're here to talk to you about HPC and Azure and two of the software tool chains that we have for either submitting workloads and jobs or managing infrastructure alongside it. We're hoping to give an overview basically of what the HPC capabilities are, how you use Azure CycleCloud and Azure Batch to manage workloads that use that infrastructure. If you have questions at any point in time, I think we're both we're both pretty interruptible, so feel free to just throw an exception or do an interrupt, and we're an interrupt-driven device, so it should be totally fine. So I'm Jason Stowe. I'm Principal Group Programming Manager for the cluster and hybrid HPC workloads at Azure. So I am used to be the CEO at Cycle Computing, which created the CycleCloud product that got acquired last year around this time. And then from a tactical standpoint, I also now manage the H infrastructure. An individual on our team, Evan Burness, has done a stellar job with that. There was some exciting announcements about it, and the relationship with Cray.
I'm Ian Finder. I'm a senior program manager in the group that produces the specialty compute SKUs like the GPU accelerated SKUs, FPGA accelerated SKUs, and the batch product, which plays counterpoint to Cycle in our high performance computing story.
Awesome. So just to get started, the reason why everybody I think on our team gets up in the morning is because a lot of HPC workloads are super motivating. So our customers do amazing things. They protect retirements that people have spent their lives earning. They are searching for new potential molecules to treat cancer via targets that have been identified through genomic workloads. They're doing various forms of rocket design in some cases. The Aerospace Corporation uses our software to manage design of rockets for both civilian and military purposes. So from a practical standpoint, it's really easy to get up in the morning. The downside of this is that these workloads are really demanding. So they're normally on the cutting edge of either performance or price targets or both. And so they normally require excessive amounts of scale, excessive amounts of elasticity in certain cases, great interconnect, memory bandwidth, so on and so forth. These are demanding workloads. And so the challenges for on-prem HPC and meeting a lot of these different use cases is that you have an on-premise cluster. I managed a Disney movie compute farm before starting Cycle. We were the 84th largest on the computer on the planet. We took down 2 square blocks of power in Toronto when we lit it up the first time, which is awkward because you can't go to lunch at your favorite place. You're like, oh, power's out, let's go to lunch. That didn't work. So in the meantime, the problem was, as big as that machine was, it was too small when I needed it most. And then when I wasn't using it, it was way too large. So in addition to being able to manage business demands, also maximizing your investment, there's now a lot of new workloads that are coming through that seem related or might be able to leverage a lot of the simulation data that we generate on these systems. And so whether it's requirements around regulation, which in financial services is driving a lot of computing, same thing in life sciences, or AI, IoT, and data analytics, there's new requirements and new workloads that sit alongside these that are both very experimental, they're highly bursty, and they feel like a really good fit for cloud. So the challenge is, how do you merge this internal on-premise environment with something that makes sense in an external environment? And that's really where the new opportunity is relative to HPC. We have, if we do this right, the ability to give you the choice between capacity, scale, elasticity, and price performance. Pick 2. And that very rarely happens. So what we're going to describe to you over the next 40 minutes is essentially how we enable that from both an infrastructure and a compute standpoint. And we're doing this by a multifaceted approach. So first and foremost, we've got a fairly detailed hardware strategy around meeting customers where they are in terms of price performance on-prem, and to try and optimize the SKUs that we're rolling out on both H and in the N series for GPU and with FPGAs, so that they essentially are leveraging infrastructure that we can buy at the scale we're buying them at and drive efficiencies down to our customers. We're also approaching the software ecosystem in an open way and have integrated with a number of different ISVs and tool chains to make it very easy to operate and manage and be able to leverage workloads themselves, the workload applications themselves. And then do all of that while bearing in mind that control is still important. The other positive thing about having fixed size infrastructure is you knew exactly what your depreciation was every year, and you didn't have to worry about going over on it. In cloud, that's a little different if you're doing it right. You still have cost controls that are required to make sure that you're giving people access to unlimited compute, but not getting an unexpected bill in the process. So relative to the VMs, I'm just going to break them up into a few different categories. We have our general fleet, which is things like A, D, E, F, G. A lot of these general fleets are geared at different RAM ratios, different processor generations. They essentially are really good at throughput-oriented calculations. So traditionally, and that's traditionally what they've been used for in cloud, a lot of people have viewed traditionally cloud as being a burst-only option. It's always better to deploy on-prem. But for burst workloads, which generally are throughput-oriented, that fleet can be used. But then we get into some really interesting SKUs, the H and N that are at the bottom. So H and N are both RDMA InfiniBand connected infrastructure that offers you low latency, high bandwidth interconnect between all of the nodes. So you can actually run MPI-oriented workloads. And with our new HB and HC, we're supporting all variants of MPI as well as a consistent performance experience, because the only thing we're doing is renting out whole machines of those instance types. So you can get blazingly fast, linearly scaling job performance on those SKUs. And similarly, the next generations of N are all geared the same way, so that we have the ability to meet CFD, FEA, reservoir simulation. You name the MPI-oriented workload, we can do a good job of performing well on it from a cost performance standpoint. And then on the N side, the same thing for GPU workloads. And then as far as special capabilities go, we now have preview for FPGA-oriented SKUs. So the exciting part on FPGAs is that Moore's Law is kind of done. You know, we've stopped the gigahertz race a while back. We've kind of topped out at different numbers. But largely speaking, those are pretty stable over time. However, a lot of the interesting work then becomes what can you do with memory bandwidth, with interconnect, and with fixed function codes that you can encode in silicon. And FPGAs offer an excellent opportunity for doing that. And then lastly, the relationship that we have with Cray is unique. So Azure and Cray are working together like no two hardware provider and cloud provider have worked together before to deliver essentially bare metal Linux clusters inside of Azure that you can leverage just like you would on your internal data sets with your on-prem cluster. But the difference is these are on the Azure network. So your cluster store that's got really high bandwidth storage can now connect to our AI services. It can connect to any of the other offerings that Azure has, including our VM SKUs. You know, you should never use a Maserati to take kids to school, especially 20 of them. You should always use the school bus. So use our general purpose VM fleets to do that, and use the Maserati for what it's good for, scaling MPI workloads like no other. That's what Cray can help you do in an Azure context, but connected to all of Azure's offerings.
So Jason talked a little bit, and we're going to continue to talk throughout this session about the ideas of elasticity and scale contributing to why the cloud has a TCO advantage for your HPC workloads. But there's one we're going to touch on really quickly as well, which is simply that you're always current. If you go out and you buy a server and depreciate it over 2 years or 4 years, at the time you bought it, its workload performance might have had a good cost. It might be, you know, relative to another platform, a good value. But as the servers get older and older and you're powering them and you're locked into them and you're paying high software license costs for the workloads that you're running on them, yeah, you're losing out on an advantage that you could have in the cloud over reserving instances for a year for, you know, $10, let's say. And then next year you take your $10 and you reserve the next instance. And although Moore's Law is something we are catching up to, we are increasing year over year as we build new SKUs. Memory bandwidth continues to go up. Many workloads are memory bound. And we're putting new special silicon accelerator platforms like FPGAs and GPUs into the boxes. So, you know, year over year, when you can re-reserve your new set of instances, you're getting a lot more for your money. And that's just a really simple thing to keep in mind as we continue to talk about the TCO advantages around elasticity and scale and bursting. So another great way for the cloud to offer a TCO advantage is with low priority VMs. And this is basically when we don't have anything else to do with our VMs, if you have a workload that you don't need done yesterday, you're doing FEA on your new car and it's got to land somewhere this week. Low priority VMs are a great way to save a lot of money. Basically, when the work becomes available to do, when these VMs become available, other customers aren't using them, you can utilize Batch and CycleCloud as workload schedulers to push your work onto them and get them when they are available. And with low-cost VMs comes the idea that the VM can be preempted if someone paying for a normal cost VM needs it. But with a workload scheduler like Batch or Cycle, your work will pick right back up, even if the VM's preempted on the next available node in the pool. We'll talk a little bit about those later, but they're a key ingredient in the TCO and performance mix to keep in mind. Another ingredient in all this is elasticity. Here you can see that there was really no work going on this day, but the next day there was some work added to a job queue. And it doesn't matter if you're using Cycle or using Batch, we suddenly burst up to 1,600 VMs. We can burst up to thousands of VMs. And when they're no longer needed, when the work in that job queue is done, we can take them back down so you're not paying for them. In this particular example, this is a financial services company, and they're running, I believe, beginning of day and end of day jobs on a specific time basis. And what you can see is their ideal number of cores to execute that job is about 150,000, and we ramp right up with a very, very, very quick delta. When the cores are wanted, they appear a few minutes later. When they're unwanted, they spin down. Customer's no longer paying for them. Customer's work got done. This is the ultimate value of HPC scheduling tools.
So the idea now is, if you look at it objectively, people generally move to cloud for 3 reasons. We've covered 2 of them. So agility is one. The ability to fail fast and not use an environment anymore. The ability to be agile in elasticity. The second reason is generally capability or scale. So this is, I need to be able to do things that I can't do on-prem, so I don't have FPGAs or I don't have GPUs. I can't get my cooling in my data center to support them, so that capability motivates moves. I don't have 150,000 cores that I can afford to pay all in for, so that I have them all the time. I really only need them, to use the example given, for a few hours at the end of every day or at the beginning of every day. Those kinds of scale opportunities. And then the last is generally data center moves. So where there's opportunities that organizations realize that basically the data center is not a business they want to be in. They want to be in the business of building products or selling services or doing other industry work. Outsourcing and moving a data center is oftentimes can be a very compelling offer. So in the HPC context, remember, this is the problem of fixed utilization versus variable cost. I'm going to walk you through kind of how this translates into a blended consumption model that allows us to meet kind of on-prem needs and costs, but yet still give you access to agility and scale. So in the data center move category, if we start from the bottom and work our way up, there's now an opportunity to buy Crays, and whether this is a bare metal Linux Cray CS, which is just like a normal Linux cluster that's got Cray software stack and management associated with it, or it's an XC supercomputer or a 3-year reservation on one of our standard fleet, you can now hit price points that are comparable to on-prem infrastructure, and I'll go through an example of this. On the agility side, we covered a bit about low prio and what have you, but the upgrade on a year basis is a very common one. So a lot of times at the movie, we had a couple generations of hardware, and we would upgrade them on a regular basis. Being able to do that potentially to the entire cluster has actually got a pretty big business advantage if you have intelligent minds that you're paying a lot of money waiting for the results that are coming out of that cluster. So from a tactical standpoint, that's an agility play. And then lastly is scale. And we've already covered that, and I think it's pretty obvious. So our offerings on the infrastructure side are really geared towards enabling you to get either extreme performance on the Cray XC side, Linux bare metal performance for various commodity workloads, on the Cray CS side, and these are dedicated fixed machines just like you'd have on-prem with very high performance storage sitting next to it, all in the Azure network and able to connect directly without WAN link issues to our other offerings. And then you have the various families of VMs for throughput and HPC, MPI-oriented workloads. What we see is on a Fortune 500 user, the blended cost of their cores and data for a given compute environment was about 3.9 cents, 3.92. And what we're actually able to achieve with Cray CS versus the system they had in-house was a 3.1 cent blended cost, and that's the all-in cost for the system, the storage, and its residency inside of Azure. On a VM basis, for VM-oriented workloads, on a 3-year reservation, you get to a 3.4 cent. For a 1-year reservation, you're paying an incremental premium over your on-prem HPC environment. So instead of 3.92 cents, you're paying 4.1, but you constantly get to upgrade that as we upgrade our SKUs. And then on an on-demand and burst basis, for this set of workloads, the cost was only 4.7 cents for the workloads that they were dealing with. So I need to grab a couple hundred or a couple thousand cores and then set it back down on Friday when I'm not using it anymore, that on-demand basis is still actually really close to on-prem infrastructure. And these are all H-based and other VM-based workloads that we're measuring in the bottom 3. So does this make sense? Does everybody understand? Okay, great, awesome. So we've got a pretty wide platform to help you take advantage of this infrastructure. And so I'll cover that just very briefly, because Ian will go into it a little bit more later. But the bottom line is we've got some great hardware, and we're going to increasingly roll out even better hardware over time. The combined teams of the Azure Big Compute and HPC folks, a lot of the other Azure people that have leaned in to kind of help with that workload internally, the Cycle people, the Avere people, having all of those people focused on HPC basically means we have by far the best and largest team of people working on these workloads. And from a practical standpoint, that's going to percolate through to the hardware. It's going to mean you're going to see constant improvements in the software layer above it, the fabric, where we have VMs and VMSS, which is scale sets to provision a lot of them. You'll see continuing improvements on boot timing and other measurements of VM performance. And then at the practical level, on the application basis, you've got 2 audiences, either kind of an HPC cluster user or IT admin, or a developer that wants to be able to enable HPC workloads from within an application. And we have 2 tool chains now to meet both of those. There's the Azure Batch and Azure CycleCloud tool chains. CycleCloud is really geared towards hybrid and traditional HPC scheduler or cluster-oriented workloads, and essentially provides templates for running many of the common environments that you can modify, but also does a lot of the right stuff to make sure that we're getting interconnected InfiniBand for the right kinds of jobs, GPUs for these other kinds of jobs, but yet you can still manage them through the job queue that you know and love and are used to on your on-prem environment. Azure Batch correspondingly has a set of developer APIs that make it absolutely trivial, so you don't have to worry about the scheduler, you don't have to worry about the operations. You have a job API, and you have some specialized capabilities, including Azure Batch AI, that allow you to run certain workloads like rendering and AI and parallel R exceptionally quickly and easily, and Ian will talk about that. So these are our software stacks. And on the storage side with this, the data layer is also critically important to consider. We have both blob storage and various flavors of SSD, including the Ultra SSD that just got released earlier this week, which is really meant for low latency and really IO-intensive workloads. But we also have VM-based file systems, so you can very easily spin up NFS mount points, BGFS file systems, cluster, Lustre, so on and so forth. And then lastly, about 9 months ago or 6 months ago now, I think 9 months in January, we announced buying Avere. They are now in public preview, so you can get access to Avere VFXTs, which are essentially a write-through cache that gives you very high read performance. We've got a number of customers that use Batch or Cycle and Avere to drive compute workloads and enable you to do that in a hybrid fashion. So to peel the onion on that infrastructure, and I'm just going to spend a second on this. If you have more questions on it, please feel free to come up or come to our booth, where Scott Joshonik actually can talk to you directly about Avere. But essentially, this is a caching layer that's multi-node. It allows you to spin up tens of thousands of cores that are all reading scene files for renders, genome files for genomic processing, design files or chemistry files for material science workloads, and be able to process them and then write the results back, but do it in an architecture that supports your on-prem file system that you already have, essentially allowing you to treat the data layer in a hybrid or edge vantage point, which is exceptionally valuable in a number of industries, and we've listed 6 of them there. So with this, basically our viewpoint is that we should be able to offer you the ability to modernize very simply from an on-prem only. And that's not to say that cloud is the answer, it's an answer. You will probably never get rid of everything you have on-prem unless you're doing a DCX move, you're moving your data center. But from a practical standpoint, most HPC clusters have multiple generations of hardware. You've got something you're buying every year, a year and a half, or every time there's a processor that's worth getting that you don't have already. You've got a parallel file system, you've got a scheduler, and you've got a set of users on workstations that are submitting jobs into it. So using the tool chains that we've described, we can now create a bare metal environment for your current refresh that's running inside of Cray if it's particularly performance sensitive, if it's something where the cost economics work out like they did for that Fortune 500 company in a way that you just can't do otherwise. We also have tool chains like Azure CycleCloud that now allow you to spin up best practice templates so that your Slurm cluster or LSF or HPC pack or what have you just come up, they work, they're operated, they're heavily automated, they give you great reporting and cost control around them. They allow you to orchestrate multiple VM sizes and things like low prio, which just to reiterate again is a great way to save costs. The one thing I loved about joining Microsoft from Cycle is that Microsoft paid attention to customers enough that they actually did low prio the right way. So they don't have variable pricing, which is the huge disadvantage of AWS Spot. It goes all over the place, and there's nothing I like better on a production workload than not knowing how much it's going to cost me to run. And then secondarily, we don't mandatorily interrupt you at 24 hours, which is what Google does for the VMs in question. They just get interrupted because, frankly, Azure is a busy place to run computing right now. So from a practical standpoint, low prio is a great facility. You can take advantage of both of these. You can have Active Directory controlling who has access to all of these environments, as well as enabling you to manage things like cost and get alerted when you're needing to. And then at the data layer, you can also take advantage of the VFXT. So you can do Avere VFXTs for Azure and have that file cache provide a very high performance write-through cache that coordinates directly with the file system you have on-prem and enables massive read scale alongside it. So you can feed lots of cores that need to run workloads and then be able to simplify the overall management of this kind of hybrid environment, which you might have when you take that current refresh and you move it into the cloud all in. When the next refresh goes, you might upgrade, you might get new VMs that we have available next year or 2 years from now, depending on how often you refresh. You may add to your Cray CS, which is also fully managed. And then from a tactical point of view, as you start moving off of on-prem and into cloud, you're also going to have new workflows, which is where you can really take advantage of Batch, which has a phenomenally simple developer API for submitting jobs directly from an application. So your workstation can be directly connected to a compute environment. You get the scheduler as a service benefits where you don't have to have administration or management of them. You still want to have IT involved because there always are good reasons to have folks that know what they're doing on the HPC side connected to your workload. But then from a tactical standpoint, it makes it really easy to leverage all of the various features of Azure, including things like low prio, but all through code.
And we'll actually show that later on.
So Azure CycleCloud, and I just want to bear in mind my time. So very quickly, we announced this late August, so right about 2-3 weeks before Ignite here. I'm going to cover all of these points, but the big one is on the left-hand side. It's a freely available tool. You can get it in Download Center. You can get it in Azure Marketplace and the Azure Container Registry. It's a web application that integrates with your Active Directory and allows you to control these kinds of HPC workloads at really large scale. The core problems that we were trying to solve, especially in the context of that hybrid environment, is let's say you're a large customer that wants to move existing strategic compute workloads to Azure. Essentially, if you're someone like this, you probably have designers or engineers that have on-prem environments, they have on-prem workstations, they already have workflows. If you're in the EDA space, as an example, or a government lab, you may have Perl scripts that haven't been touched in 14 years that just work, and so you leave them that way. And essentially what CycleCloud solves first is the ability to run that environment in a hybrid way using infrastructure from Azure and manage it over time. So again, it's about making it so those workloads move as is. You do not have to rewrite them. It uses the ability to create and leverage templates that we have. We have a GitHub community site as well, so you can contribute templates back for new workloads, and we're constantly looking through that to figure out, okay, should we take one of these and actually move it into something that ships with the product? And then be able to manage both the job submission in a hybrid context, but also the data pieces. So if you had like an Azure cache, for example, you may want to tickle a directory on the other side of your WAN link to make sure that the cache is full by the time the jobs get there to run the workloads. These kinds of activities are things you can do easily. And then secondarily, we also add a heavy amount of governance and control. So you can both manage who has access to these environments, but also be able to manage what scale they're allowed to run at, and when you get alerted for how many dollars have been spent, as well as dealing with various compliance audit and reporting functions that are oftentimes needed for kind of global 2000 HPC workloads. So as a specific example, we've got a large customer that has essentially is using a template we've created that enables a multi-component system, including file systems and compute environments that are running on LSF. And we can spin up tens of thousands of cores in 10 to 20 minutes. These kind of large-scale, large elasticity environments literally can be created and then torn down in a consumable fashion. That auto-scaling also allows you to take advantage of multiple families and multiple regions, so that if you want to have geographically dispersed and guaranteed capacity, so if something happens over here, it doesn't, some of these workloads that you might have at banks or at other government institutions may have requirements, regulatory requirements around how often they're run and that they run successfully. This entire kind of environment of multiple clustered components can be entirely scripted. And that's everything from the schedulers to the file systems to license managers. Everything can be entirely done in a way that isn't ARM. It's a little more Linux user-friendly, so it's essentially like a Linux admin would expect it to be. And then just also be able to handle various use cases within these clusters so that you're setting them up like, I want my file system to have multiple, 2 copies of every piece of metadata, or I want my scheduler to have 2 head nodes and be able to monitor that they're both up and running. We handle that for the components that we operate, and then enable you to control who has access to them and what scale and spend they're allowed to run at. So right now, what I'll do is I'll give you a demo very quickly of Azure CycleCloud, and then I'll give it over to Ian. So this is the UI when you log in. You log in through a standard username password that's connected generally to Active Directory, and from a practical standpoint, once you're in here, you have all of the clusters that you're currently configured to manage, and this is everything I have permissions to see and interact with.
It's not coming through.
Uh-oh. Okay. I wonder, yeah. Well, it wouldn't be a demo if there wasn't something wrong. So
And the PowerPoint.
let's just take a look at this and this. All right, there we go. How's that?
Great.
Perfect. Okay, guys, great, terrific. So this is the home screen that essentially shows you every cluster that you're interacting with. I'll walk you through the process very quickly of creating a new one. So we have all of the available schedulers that are commonly used in HPC. So this is things like HPC Pack, PBS Pro, LSF, Condor, Slurm, you name it, Symphony. All of these can be quickly and easily created. You can also package up file systems, and we ship with a number of default file systems. You can tweak all of these. These are all essentially text files that describe, and there's a couple of other markup language-oriented files that describe projects and clusters and how you roll them out, and basically leverage DevOps facilities that you may already have. So if you use Puppet or Chef or Ansible or any of the other Salt tools to do that, you can hook them right in. This is the Salt script I want executed whenever a node comes up. But the other things we're doing on the back end is we're actually checking the nodes for a lot of errors that happen, generally speaking, when you're dealing with virtualized infrastructure, so that we can handle them automatically and not put them in a production environment unless they're already working. Batch does the same thing too, by the way, so both tool chains do this. Once I have this environment, if I want to spin up, for example, a grid engine environment, I can name it. I can turn around and specify which system I want, which region I want to be able to run in. I can say, look, the head node, I actually want a 12-core D-oriented machine, but I can actually get access to. Yeah, sure, absolutely. The question was to zoom, which is a great. Actually, let me do one thing. Let me close the dialog and then zoom in. So essentially, you can get access to all of the different VM types we have, be able to say, look, I want a compute-optimized VM that's going to be an F, and this is what I want to auto-scale with, so on and so forth. All of these settings are just entries in a form, so you can remove them or expose all of the ones that we have. This is a subset of our standard grid engine cluster that we ship with. You can control the scales at which these operate and handle things like low prio. Apparently, I already have a demo Ignite page here, so I'll skip through that. And then, tactically speaking, there's some networking. Which subnet do I want to be able to execute on? I'm going to do my this given subnet, and I click Save. And there are a number of advanced settings which you don't have to touch, but you can if you want. And I can click Save, and then I have a cluster here. Now, before I start it, what I may want to do is say who has access to it. So I can essentially add either an OU group or individual users or lists of users and say, I want Adrian, who's working on this project, to be able to have an admin level role relative to the data endpoints and the compute for this cluster. You can also add OU groups in general for all your HPC sysadmins. And then I now have a cluster that's been shared. I might also want to create an alert to say, look, I only want, as an example, $10,000 worth of spend in a given month for this. And if we go above that, I'd like to know as soon as possible. So you have the ability to essentially add alerts around HPC job level spend. And then you can click Start, and we'll kick off creating this environment in that subnet, in that region, with that infrastructure. And you could then log in and start submitting jobs and doing everything else that you would normally do. I actually have an environment that was used to run NAMD that's been operating for some time. And essentially, this is in the process of spinning down in various respects. So this set of, this infrastructure itself was doing nothing until jobs were submitted earlier today. And you can tell, we have hundreds of VMs, all the way up to several hundred VMs, all being created and deleted. And you can see the notifications here to make that easy. So essentially, the goal here is to make it very simple to create these clusters. You can look at information about what jobs are running. I now only have 24 tasks left in this environment, which is why the environment's spinning down. You can see a jobs page that gives you at least a general overview of the scheduler, and then be able to deal with, for example, event logs of everything that's happened in this environment from a regulatory standpoint. So this is every action taken against these HPC clusters, who it was by, when it was done, so on and so forth. If you have more questions, let me know. And I'm going to move back over here. And there's a bunch of other capabilities that I didn't get a chance to go into. This is things like national cloud support, and there's an API for clusters themselves. So if you don't like how we're auto-scaling Slurm, you have some special use case and you want to code to it, there's Java and Python that you could write that's very simple to change those behaviors of our orchestrator. And then from a tactical standpoint, the goals, again, are just to provide a very easy set of tools for managing workloads using templates that are already built and already work in a best practice manner, provide IT the ability to manage these workloads overall, and then enable organizations to link usage and spend and use Active Directory to put control around that. And so that's basically what CycleCloud does.
All right, great. Let me see if I can power through this in 10 minutes. So in counterpoint to CycleCloud, which is what Jason was talking about, which is really great for like lift and shift scenarios, hybrid scenarios, established compute workloads, we've been working in Azure to provide developer and partner support for a service we call Azure Batch. And this is for your more cloud-aware scenarios. It's got an API. It's more intended to be coded against as you build your workflow. So in these workloads, pretty much any HPC workload has an input set of data and an output set of data. This is data you want to stick around even when your cluster's not there. Because when your cluster's up, you're paying for a bunch of compute resources. But in an example of like the film studio example, the input data would be your scene files, your textures, the stuff the animators are working out of. And the output would be the rendered frames of your motion picture. The same model sort of applies to fintech and to other workloads. In a Monte Carlo simulation, you would have historical data from a day of trading in your input container, which can be a Vir, it can be Azure Blob, it can be whatever you wish that you've persisted, and then you run an HPC job on it and store the output. Let's talk a little bit about how certain things parallelize. In the example I'm going to show you in a little bit, we're going to transcode a bunch of video files. In this example, a job is the transcoding of a set of files. In the Monte Carlo simulation example, a job might be simulation F, and within it you have all these tasks. Let's say you're doing your end-of-day risk analysis. Each one of these tasks might be running on an individual node, and that task might be, look at this section of the day, look at this section of the day. And we'll see in a moment how this parallelizes. Basically, on each worker, you're going to be invoking a set of parameters that point it at that range of data. We can call that a task. So every HPC workload that follows this model, you have your application, and this is what you're distributing across your pool of VMs, your multiple hosts. Then you have the VM itself. This is that dynamically sizing pool that we talked about. And then you have a queue of jobs. The job might be, again, run my end-of-day numbers for this day, run my end-of-day numbers for this day. And within each one of those jobs, there are tasks, which are the little tiles. A task might be render the first frame of my movie. Another tile might be render the last frame of my movie, and that job could be a movie. Or better yet, that job could be a scene. And the tiles are the frames within it. Each tile gets put onto a specific VM. That VM invokes your application with a set of arguments around it. Like we talked about again, there's storage. You persist data on the input path, you persist it on the output path. And what we do in Batch is we provide you job scheduling and VM management so that your application doesn't have to deal with the nuances of bringing up the VMs, making sure they're networked, and dividing all the work around. And I'll show how that works in a moment. But there's a tremendous amount of cloud value for HPC workloads that we already kind of touched on. I'm not going to go into depth on this slide, but the scale, the elasticity, and then two that I really like to call out are the fact that not only do you pay for only what you're using, but you know what this costs. When you run a job through one of our workload management tools, like Batch or like Cycle, you can look at your end-of-day portfolio risk analysis simulation, for instance, and you can say, okay, this costs me $1,000 to run. And more than the actual fact that it's pay-as-you-go, that known cost factor is key for a lot of organizations. There's also the reach and locality, which in our movie example is really key. You can use our virtual desktop infrastructure to work on and do your modeling on that data set in the same place that you're rendering it from or processing it from. So the platform looks something like this. At the bottom is the hardware, and these are the specialty SKUs that we've been talking about, our GPU SKUs, our high memory bandwidth SKUs, our compute SKUs. And on top of this is our core cloud services and VM infrastructure. This is where magic like networking and storage happens. This is sort of the base Azure plane. And then on top of it, because we want to make it easy for you to manage your clusters, we don't want you to have to say, this VM has this IP address and is part of this pool. We've built these tools, Azure Batch and CycleCloud. And they're positioned accordingly. As I said, CycleCloud is more of a lift and shift and hybrid kind of thing for taking well-defined HPC workloads. But let's say I'm making a media transcoding service. That's what my example is going to be. I want a media transcoding service, and when there are videos that need to be transcoded, I'm going to spin up a bunch of VMs, and I'm going to transcode in parallel. When I'm done, I'm going to take them all down. So there's a bunch of different tasks this works for, and we've touched on a lot of them, so I'm not going to go into it. I'm going to go straight into the demo in the interest of time. So we've actually built a media transcoding service on batch in about 150 lines of C#, and I think it's really kind of a neat demo. Here I've got a pool of VMs, and 10 of these VMs are low priority, so I got them because I have them. They're here. I can do things faster because I got those low pri VMs. And the other 10 are my dedicated baseline capacity because I don't want my service to stop going just because I don't have low priority VMs available. When we went back to that resource management graph, I'll show a little bit about that later. But what I'm going to do is I have, in an Azure storage container, I have my persisted input data. So even when the cluster's gone, all this data is going to live here. And this could be a Vir, this could be Azure Blob. In this case, it's Azure Blob. And I've got all these cool Azure talks we did. And I want to transcode them all because I want to watch them on my iPhone. So up here in Visual Studio, I actually have, in 150 lines of code, a batch client that we've written, just to show you nice people. And what it's got hard-coded in here is a batch account name and a storage account, which is that storage container where all my videos are. And I'm actually just going to step through this. When I hit play, it's going to start a batch client and attach to that pool that we had that I showed you. Of course, I can make the pool if it's not available. I'm not going to do that. There's code in here to do that in that 150 lines if the pool wasn't already up. And I'm going to make a job, and I'm going to call it FFmpeg plus my name plus the date and time that it's at now. And then we talked about those tasks, those individual tiles that get distributed to each VM. So in this case, there's going to be a task for each one of those 21 videos I want to re-encode. And when I hit the play button here, you'll watch the little count of that variable increment in my Visual Studio instance. I'm adding tasks to that job. And when that count hits 21, it's going to submit that job to my batch pool. So there'll be a job with the name FFmpeg in my batch pool with 21 tasks in it. Let's just go ahead and finish that out. All right, so my program exited. And now when I switch back to my pool view in a moment, you're going to see this actually doing something. Now, it hasn't quite taken yet, but in the meantime, I'm going to show you the nodes. You see these VM names, and if I scroll over, there's IP addresses. This was all done by batch transparently. You don't have to worry about assigning names to your VMs. You don't have to worry about configuring the network. It all happens for you. And if I go back to my cluster overview, now you'll see this heat map. You'll see that they're actually running my FFmpeg re-encode jobs. So 150 lines, I've built a service that can take video and transcode it in a cloud-aware fashion that capitalizes on elasticity, on low priority, right here in Azure. And you're going to actually see them finish. Each one of those tiles is starting to finish. They're going from running back to idle. It's all just totally magic. So as those finish up, I can go back to my persistent storage container where we're storing that input and output. And I can go ahead and I can just refresh this here. And you can see from these modified times that they were all modified. And I'm sorry, my clock on my PC is Pacific time. So, but you can see that they were modified just now. They've all been re-encoded. OK, great. So I'm going to switch back here. And I want to touch a little bit more on that low priority model, because we talked about running a service, and certainly it's not suitable to have a service that waits on low priority, right? People are relying on me to transcode some stuff. If low priority becomes available, I want to do that work faster, and I want to do it cheaper, because low priority is available. But I certainly need to always be doing some work. So that's this first one, lower cost with guaranteed baseline capacity. It basically says, I'm going to have 40 VMs up for my transcoding at all times. But when low priority comes into play, if I have extra work in my queue, I'm going to burst it on low priority. I'm going to pay less for it, and I'm going to get it done faster. The other model here is, maybe I'm just re-encoding these videos for Ignite next week. Maybe I don't need them tomorrow. Maybe I don't have an SLA on my customer. Well, in that case, I'll just wait for low priority nodes to become available. Batch will automatically pick them up, give them work. If they get preempted, no big deal. And I'll pay the absolute lowest cost to have that work done. And then finally, there's low cost where I maintain capacity. And that's basically, I know how much work I need to do, and give me low pri when it fits. So there's some really cool cost and optimization models you can do with the ingredients of batch and cycle around better utilizing our specialty SKUs and our low priority and things like that to really drive down the TCO of your service. Before I go, I want to mention one other thing. I got 10 seconds left, but for our motion graphics customers, we've started a model that we hope to see in other batch workloads too, which is pay-per-minute licensing. So if I'm making a feature motion film on my laptop and I need 10,000 cores to render it, I only really need them for like a day, right? So I'm not going to go pay for a 1,000-core mental ray license. That would be totally insane. It would be not cost-effective. So what we've done is we've partnered with some of these render companies who traditionally have pay-per-core licenses, which are not flexible and not good in the cloud. And instead, we've offered pay-per-minute licensing so that you can burst on Azure Batch in the cloud and not have to buy these inflexible license terms that don't work for that kind of scenario. So this is really cool. And to highlight how easy it is to use Batch, many of these, like this example here in Maya, have a batch client built into the application software. So right from Maya, you can say, I want to render all this stuff. Let me put these settings in. There's a little C# plugin in Maya. You hit Submit Job, and it kicks off a batch render with pay-per-minute licensing and all this stuff. So this is an example of a service that has been built on batch. And we're hoping that because there's this inherent flexibility, people get creative and build many more. OK. That's all I had. You're talking lift and shift of workloads with a compliance issue?
I'm talking lift and shift of workloads, not so much compliance as the cost of purchasing express route doesn't make sense from first to try.
Oh, that's true. I think a veer for some scenarios, I mean, it's obviously going to change based on your scenario, but having that right through cache like a veer in the cloud is going to provide a lot of value.
The networking concerns of lift and shift when it comes to HPC in the cloud?
So I think it depends on the scale of the data you're talking about. Really, but if you look at data sets, generally there's a lot of opportunities in them. So let's say your data set's small. Then you can trivially burst because it's a non-issue. It just transports its megabytes, gigabytes. It takes very little time. Let's say you're at the terabyte range. So you're in the middle somewhere. You've got single-digit terabytes are still kind of transportable depending on what your internet connection is and what your home connection's like. But from a practical standpoint, like
it's relatively low security. These are some very, very high-value data sets you're describing at the beginning.
yeah, yep.
Well, I mean, certainly you can encrypt on the way up, which is something we encourage.
And in those scenarios, yeah, you definitely will use a transport layer that has encryption in it. So nothing's ever in the clear. You would have a shared secret workload where you're encrypting, transporting the key separately, decrypting, re-encrypting the results, transporting the results, and decrypting back on-prem. So those scenarios are well-worn. At Cycle, we had customers doing that, like Johnson & Johnson and NASA and Aerospace Corporation, which makes rockets for some reasons you can find out about, but for some that you can't. And they didn't have dedicated connections to the internet at the time, to cloud providers at the time they started running these in production. So it's possible to solve those problems. If you're in the really high-end range where you've got petabytes of data, then you have another positive effect to data sets that comes into play, which is large data sets tend to be partitionable. So what you might have is a set of users that are working on several different things that all have, in aggregate, 15 petabytes of data. I was dealing with a customer at this number before. But what the HPC admin on that side actually identified themselves was, this 15 petabyte data set actually has 20 different parts to it. And so I can deal with them separately by having some of my workloads run on-prem on the bare metal instance I have already, the cluster I already have. And I can have some run off-prem only and have it so neither the twain shall meet. You could also use things like Databox to do bulk lift and shifts and uploads of data. So that's one of the edge tools that we have that can move hundreds of terabytes to petabytes to tens of petabytes of data in a physical form. So never underestimate the bandwidth of a station wagon full of DAT tapes, if I'm remembering my quotes correctly.
Yep. Hurtling down the highway.
So that's the other option you have. But the answer is that the devil's in the details. The good news is we have a really large team, a global team that can help you sort through that. So you can reach out to me directly, and I can make sure we get the right people from an HPC architecture standpoint in. Our global black belt team is really good. The CAT team that we have, which kind of works on advanced problems that's geared towards HPC, is stellar. CAD, it's like
Customer advisory team.
Yeah, so from a practical standpoint, we have people to help you solve these problems. But regardless of what end of that spectrum you're on, you just might use different tools and different technologies.
You can even use open source tools. Nothing says that the cluster you're bursting your compute on has to be, you can have a separate set of storage nodes running whatever open source thing you desire, backed by our infrastructure boxes with SSDs, whatever you need, talking to your stuff on-prem and handling that middle part.
That's where one of the Cray use cases is too, is on the high end of those data sets where the data sets are really, there is gravity around them. And so if you face a problem where I've got a dedicated HPC cluster on-prem with tens of petabytes of data or multiple single petabytes of data, and you don't want to be slinging that around very often, but you still need access to IoT processing, FPGAs, and GPUs that you don't necessarily have high amounts of variable capacity on-prem for, that becomes a candidate of looking at that HPC cluster, and we have programs, and I own this relationship, so you can talk to me about it. But we can basically take a look at your on-prem cluster and say, look, let's move that into a Cray off-prem in Azure. It's still a bare metal cluster. The performance is amazing. The cost performance can be amazing as well, and you can tweak that. And then all of the other Azure services, you have no charge on the network to access them because they're on the Azure network. So those petabytes don't need to be moved. They can just go spin up VMs that will pay attention to that data, or use our AI service or Azure Functions or any of the other things that we have to pay attention to that data set. And that's, again, all within Azure, all within your subnet. And again, there's reference architectures for the security on this. We have customers doing it that are very happy with the security story around it.
And really do look at the Databox product. I don't know how much that's been touted externally, but I know those guys pretty closely, and it's a really neat thing.
Dean
this use
does
case.
a great job on that one. Yeah.
Yep.
Yep. Great question. Any others? Yep. Yep. Mm-hmm.
Well, yeah, first of all, you're going to be using the same. The only thing that really changes, like in that batch demo, is literally you can constrain it all the way down to the invocation arguments that you're passing the process. So you can use the same base VM. You can do it on the same VM SKU type. You can do it with the same drivers, same everything. I mean, you can literally constrain all of those things. And the only thing that changes is that worker, the task, the tile that they're running, just the arguments that get passed to that through the batch API. Everything else, the operating system, the driver, whatnot, that's all going to be the same. So in the cloud, it actually makes it super easy because you can package up your whole environment with your drivers, with your NVIDIA CUDA support or what have you into an image. And that same image that they're developing on, you can deploy through batch on a private subnet as your cluster.
So that's
right.
Yep. So yeah, for the other use case, so there's a similar corresponding. So almost every question that isn't just data related, because data kind of applies to both of us, but every other question also applies to both of us. There's a similar notion inside of CycleCloud where if you're using a scheduler like LSF that has great support for I need an SSH connection into an execute node so I can do some work, and then I'm going to go submit a job, you can do that same activity on LSF in the cloud, or we can add the nodes to your internal pool using that reference architecture that I described. And again, the devil's in the details in terms of just understanding what your user scenario is. But we do have numerous customers that use either VDI instances or raw execute nodes that are in a mirror copy of what you have on-prem. So the workload can run here, it can run here, and you can still get an individual session that's dynamically created easily.
And there's actually an option in batch too. If you happen to use that, we NAT like all the SSH port. You can put in a custom rule so you can get on the box for debugging while it's running, even though it's ephemeral.
Same thing with licensed codes too. So on both batch and cycle, you can essentially phone home through environment and proper setup of your subnets so that all your FlexLM calls go back to the same nodes, so on and so forth. But we could, I don't know what scheduler you're running and how that workload works internally, but if you're on an internal HPC cluster and you want to be able to run the same job, that's a well-worn use case. We'd be happy to help you there. Yeah. So you did. That's what I had spun up there. That had the 200 nodes was a grid engine environment, and that environment is an auto-scaling environment. We can also create a node array for nodes that are only used for development sessions. So that way you're guaranteed you always have some empty capacity. I want a two-core VM available for people to use, and then when someone uses it, i.e. grid engine claims it with a job, then we'll spin up the next one. So you can do workflows there that make that really easy, but yet it's still a part of your grid engine environment that you have on-prem. Yeah. Any other questions? These are all great. Awesome. Well, I hope you guys are doing some really cool stuff, and we hope to be able to help you. We always love hearing what users use us for, so feel free to come up and ask further questions. I don't know.
Get a card or something if you have any further questions. We're happy to help.
Yeah.